January 1910. Halley's Comet is about to return. And this time, say scientists, the Earth will pass through its ghostly tail. With each passing week, this mysterious visitor becomes an ever bigger story. Comets have long been linked in people's minds to catastrophes of one kind or another. Plagues, wars, the death of kings. Even some scientists are concerned. A French astronomer, Henri Deslandres, warns of dramatic changes in weather. And indeed, just weeks before Halley's arrival, Paris is staggered by the worst flooding it has seen in decades. Deslandres' colleague, Camille Flammarion, has an even graver worry. He fears gases in the comet's tail might combine with nitrogen in the Earth's atmosphere to produce enough nitrous oxide, or laughing gas, to cause contagious gaiety, paroxysms of delight, and in the end, widespread madness and death. In 1910, comets are almost as mystifying as they were when 17th century British astronomer Edmund Halley realized that one in particular returns to the center of our solar system every 76 years. As Halley's namesake approaches, the excitement, anxiety, and business opportunities grow. But then, when it has come and gone, it is science, not superstition, that claims the day. Using newly developed tools, scientists gather photographic and spectrographic evidence that proves the comet's tail is too diffuse to affect our atmosphere, and that its icy heart is but a tiny fraction of the visible whole. As the 20th century dawns, there's a growing sense that the mysteries of our universe aren't as far beyond our grasp as we once believed. In my grandfather's time, at the turn of the century, the night sky is the greatest show around. It plays week after week, even on Sundays, assuming the weather holds. Part of its power is its infinite mystery. No one knows where stars come from or why they shine. Few believe we will ever understand what the universe is made of, what the true nature of matter really is. But then, within a few years, all hell breaks loose. There are revolutions in astronomy and physics, and long-cherished ideas are shattered about the nature of the universe, of space and time, and even reality itself. The only thing that remains the same is the glory of the view. From the moment the telescope is invented, it's our window on the universe. In the 18th and 19th centuries, ever larger and more elaborate telescopes reveal ever more stars. By the end of the 19th century, telescopes are so large and reveal so many stars, astronomers are working overtime just to catalog them. There seems little need to build even bigger instruments if all they can do is find more stars to catalog. But George Ellery Hale disagrees. He's passionately convinced a big enough telescope will change astronomy in ways it's impossible to anticipate. And he's determined to make that happen. That passion brings him to Mount Wilson in Southern California, where the air is almost always free of turbulence and clouds. It's the perfect spot for an observatory. With funds from the likes of steel tycoon and philanthropist Andrew Carnegie, Hale sets out in 1908 to build on Mount Wilson the world's largest telescope. The instrument he envisions will be almost twice the size of any then in use. It will collect and focus light with a mirror 100 inches wide. Hale's enthusiasm is infectious and persuasive. It also masks the enormity of the technological challenge he's undertaking.
Nobody is pouring glass, molding glass at the size that's going to be necessary. Nobody is creating the kinds of beams and girders and the superstructure that's going to be necessary. These things weigh hundreds of tons, thousands of tons. You also have the difficulty that they're located on mountaintops. You have to build the roads. You have to build the living quarters for the astronomers. You have to have machine shops on site. It just goes on and on and on. These are almost kind of technological kingdoms in their own right, and they've never been designed on this scale before.
Things seem to go wrong from the start. The mirror has to be the largest solid piece of glass ever made. A French glassmaker pours enough green glass for 10,000 champagne bottles into a huge mold and then packs the whole thing in manure to slowly cool it. Unfortunately, it comes out flawed. Twice more they try, and each time the giant discs crack as they cool. Lacking the money to try again, Hale orders his opticians to grind the first, in the hope its flaws aren't fatal. It takes 4 years of grinding and polishing to finish the mirror, and even longer to build the rest of the telescope and its dome. Hundreds of tons of steel and concrete are hauled up the mountain road at a cautious 10 miles per hour. Even at that speed, accidents happen. The steel sections of the telescope itself are built at an East Coast shipyard. Some are so big they must be shipped by boat to California. World War I has broken out, and German submarines are a constant threat. Long prone to bouts of depression, Hale's worries about the project begin to affect his health.
Later on, he admitted that he had been visited by a companion, sort of described as a little green elf who might come to his bed or sit on his shoulder, perhaps to give him advice about how to run his life, how to raise money, who to talk to. It's hard to say. The elf perhaps helped him work out some of this stress.
Whatever it is that carries Hale through, on November 2nd, 1917, the 100-inch telescope is finished. Its 100 tons of iron and steel move with the precision of a fine watch. Its 9,000-pound mirror can detect a candle 5,000 miles away. What Hale has built is one of the marvels of the 20th century. It will reign for decades as the best telescope in the world and prove beyond doubt the worth of big telescopes. To spend a night here is the dream of astronomers the world over.
You would open the dome, a kind of rolling like thunder, and you were alone on the mountain with a telescope. It's just you and the universe, or you and God, so to speak.
You'd sit at the platform at the telescope, guiding, making very fine adjustments on this magnificent instrument with a little hand paddle, with your eye staring down onto the illuminated crosshairs, and work there 8, 10, 12 hours.
Oftentimes it was extremely cold. In winter they wore heavy coats, sometimes they wore bearskin or sheepskin coats. You could literally have your tears freeze to the eyepiece, and they wanted hot coffee, but Hale wouldn't allow it. He thought it was poisonous to the system.
Easy, 20 hours.
Coffee isn't all that Hale keeps off the mountaintop.
In the 1920s, I would not have been allowed to work up here. In fact, I wouldn't have been welcome even as a wife or a visitor of any of the scientists. Hale, in his days at Yerkes, had found that the wives of some of the astronomers became a distraction to their monastic scholarly studies, and so they were essentially banned from the mountaintop.
Ironically, without the contribution made by a woman, the first great discovery made with the 100-inch might not have been possible.
The closest a woman could get to the field was, at the time, at the Harvard College Observatory, where major data collecting projects were in progress. Women were hired on to help to analyze the data, to do all the menial tasks that were below the duties of the men.
Henrietta Leavitt is one of a dozen women who studied tens of thousands of photographic plates taken by men at distant observatories. Leavitt's task is to examine plates taken at different times and look for stars that vary in brightness. She notices a pattern in one class of stars, called Cepheids, and realizes the time it takes them to reach their maximum brightness can be used to determine how far away they are. It's a landmark discovery. Before Leavitt, astronomers couldn't calculate the distance to any but the closest stars.
What Henrietta Leavitt did was provide one of the first, and still to this day, one of the most fundamental yardsticks in the universe. It is the measure by which all distances are determined. Without that, we'd be clueless.
All the astronomers George Hale brings to Mount Wilson will, at some point in their careers, make use of Leavitt's celestial yardstick. But there's one for whom it will have special significance: Edwin Hubble. A star athlete in college, Hubble had won a Rhodes Scholarship and studied law at Oxford University in England. Upon returning home, however, he decides against becoming a lawyer and heads off to graduate school to take seriously a fascination with the stars that he has felt since childhood. When Hubble arrives at Mount Wilson in 1919, he's a smart but arrogant 29-year-old who has taken pains to adopt what he sees as the proper image of an astronomer.
What he tries to do is to create this portrait of himself as a kind of natural-born patrician. He tries to lose his Missouri roots because I think he's embarrassed about those things. He sees the English gentleman as being the prototype of what he wants to become. He wears English tweeds, he wears knickers, which have gone out of fashion except on the golf course. He smokes a pipe.
He spoke with an affected British accent. He had dueling scars, which were said to be self-inflicted when whispered among the staff.
He loves being separate and apart from his fellow human beings, and he plays that to the hilt.
In time, most of Hubble's personality quirks are overlooked because he's an excellent astronomer with a gift for asking the right questions. Hubble wants to unlock the secrets of the nebulae, faint, fuzzy smears of light that have puzzled astronomers for 1,000 years. Even with Hale's magnificent 100-inch, their true nature eludes him for 4 long years. Finally, in October of 1923, while photographing one of the spiral arms of the great nebula in Andromeda, Hubble catches a break
He took a 40-minute photographic plate and developed it the next day and looked at it and thought he saw what was then known as a nova. That was another hot topic. That is, what were novae, what were stars that brightened unexpectedly. So his curiosity piqued. He decided the next night, which was a better night to take another exposure, and took a deeper photographic plate.
This plate has what he believes are 3 novae. Yet an even greater surprise awaits him.
Well, when he got down to the mountain the next day and he began to compare the plates with those that had been taken earlier, he discovered that one of the 3 novae was not in fact a nova, but it was a Cepheid. And it's a eureka moment. He writes in capital letters on the slide itself, VAR, exclamation point, for variable star.
Hubble knows instantly, thanks to Henrietta Leavitt's discovery about Cepheids, that this star and the system it's a part of must be very far away, and the universe must be far larger than anyone had dreamed.
Yeah, it must have been a good moment for him. What he found was that the distance to M31, the Andromeda galaxy, one of, turns out, our nearest neighbors, is about 2 million light years. So people had been talking about the scale of our galaxy, 10,000, 20,000, 30,000, maybe 100,000 light years. What this meant was that M31 and all those other galaxies were not part of our system. They were themselves big systems equal to the Milky Way.
There are, in fact, billions of galaxies, each one containing hundreds of billions of stars. Hubble's discovery of the stunning size of the universe and the multitude of stars and star systems that can be found within it changes forever our picture of the cosmos. That discovery alone would have made Hubble one of the great astronomers of the century. But he continues to study distant galaxies and makes an even greater discovery. For 5 years, he gathers data on the movements of galaxies, recording where they're headed and how fast. If a galaxy is moving away, its light is stretched. The interval between wave crests gets longer. The light appears redder. The faster it's moving, the redder the light. If a galaxy is moving closer, the light is compressed and appears bluer.
After many years, Hubble could sit down and look at this great quantity of information, and he plotted a chart. He plotted for the nebulae the motions against the distances, and he found something truly amazing, a straight line.
He found that the distance of a galaxy is proportional to its velocity. So as you go twice as far out, turns out the velocity is twice as big. You go 3 times as far out, the velocity is 3 times as big. We live in a world, I mean, a big world, and a universe, where everything's rushing apart, and it's happening in a way we call Hubble's law, where the velocity is proportional to the distance.
An expanding universe. How could that be when the whole history of human thought assumed, just took for granted, that the universe is this fixed thing, and how could it change? The universe is everything. How could it have an evolutionary path? Because if you had an expanding universe, that might mean it had a beginning. It might mean it'll end. This is a discovery for the ages.
Before Edwin Hubble's discovery, even the great physicist Albert Einstein assumed that the universe is fixed and eternal. His original equations for general relativity had predicted a changing cosmos, but Einstein was unable to believe his own theory. So he added what he called a cosmological constant to bring the universe to rest. Years later, in 1931, Einstein travels to Mount Wilson to meet Hubble. While there, Einstein declares that his cosmological constant is the greatest blunder of his scientific career. Of course, by this time, Einstein can afford to admit to a mistake or two. He's already renowned as one of history's greatest scientists, the man who redefines gravity, space, and even time. At the age of 22, at the turn of the century, Albert Einstein is living in Zurich and facing an uncertain future. He dreams of becoming a professor of physics, but he can't get a job. He has alienated most of his college teachers, and they won't give him the recommendations he needs. In early 1902, he moves to Bern. He's tired of scraping by with what he can earn giving private lessons, and a friend's father has offered to help him get a job there. It's with the Swiss Patent Office. He's a technical clerk, third class, reviewing applications for patents on new inventions.
Einstein was a perfect fit for his patent work. And those patents that he considered were, in my view, absolutely formative of his scientific style. He'd sit down every day with stacks of documents, and his job was to strip away all the complications, to take a patent like this and figure out, did this violate the basic laws of physics? What was its central idea? Was it that central idea new, or was it something that had been known? And those sorts of decisions, which he made every day, looking at these new devices, shaped his sense of how to strip down a physical problem down to its absolute essentials. What are the principles?
It's this same approach that compels Einstein to re-examine fundamental assumptions of classical physics, including ideas about space and time that seem to everyone else inescapable. In the early 20th century, everyone, from physicists to sports fans, takes for granted that a mile is a mile, no matter where the race is run. That the runner who finishes in 4.5 minutes is faster than the one who finishes in 5. Common sense tells us that time and space are the same everywhere and for everyone. Indeed, that was Isaac Newton's starting point when he wrote down his laws of motion and gravity in the 17th century. Laws that seem to explain everything from the flight of an arrow to the orbits of planets. But Einstein is willing, where others are not, to question everything, even our common sense view of the universe.
All I have tried to do in my life is ask a few questions. Could God have created the universe any other way, or had he no choice? And how would I have made the universe if I had the chance?
Einstein is driven to ask such questions by a problem he sees with the traditional description of light.
He knew from Maxwell's equations, from the great classical physics that had preceded him, that light could be understood as a wave, and that every time you saw a wave of light, it was always traveling by you at some enormously fast speed, like 186,000 miles a second. So we were always in the position of somebody, say, standing on the beach, watching a train of waves go by. Now, with any kind of wave that you've ever seen, or Einstein had ever seen, you could always catch up with it if you went fast enough. If you had a bunch of waves going down a canal and you got on your horse and rode alongside it, you'd see the wave just frozen, as if it was not moving, because you'd be moving with it. And Einstein's thought to himself was this: what if I caught up to a light wave? What if I went as fast as light was going? Would I see it still the way the horseman sees the waves in the canal if he catches up to it? And then he thought to himself, well, that would be such a strange sight. It doesn't correspond to anything anyone's ever seen, a still wave of light.
Einstein is convinced that light wouldn't be light if you could catch up to it. But in classical physics, you can catch up to any wave, and light is a wave.
How could it be that there was a wave moving along that you couldn't catch up to? He didn't know how to solve the problem. He didn't even know how to articulate the problem fully, but there was something wrong.
Children who wonder about things like light, time, and space are satisfied with the stock answers and never give them another thought as adults. But because I was a late developer, I first pondered such simple questions as an adult, and so probed them more deeply and tenaciously than any child would do.
In order to simplify the problem he sees with light, Einstein uses a series of thought experiments that take place only in his imagination, like a journey on a train.
From James Clerk Maxwell's equations, we know that the light reflected from my face traveling toward this mirror must move at 186,000 miles per second. Okay, Einstein said, but what if the train were moving at the speed of light?
One possibility is the train catches up to the light waves, so they never reach the mirror. But Einstein is convinced this can't happen. Light can't stand still.
And what does it mean if I do see my reflection in the mirror? Well, from my point of view, everything is just fine. But for the person standing outside of the train, there's a problem. That person sees the train moving by at 186,000 miles per second, and therefore the light reflected from my face traveling toward the mirror must be traveling at twice that rate, or 372,000 miles per second.
372,000 miles per second is the speed of light added to the speed of the train carrying the light. Physicists have added speeds this way since the days of Galileo. But Einstein concludes this simple adding of velocities is wrong, because the speed of light never changes. It's always 186,000 miles per second, even if its source is in motion. Whether on or off the train, you have to get the same measurement for the speed of light. The stunning consequence of this is that someone off the train measures rulers on the train as short and clocks on the train as running slow.
In a flash of brilliance, Einstein proposes that distance and time are not absolute, that a foot and a second measured on the train are not the same as a foot and a second measured off. Distance and time are relative.
Hold on. We're taking off.
Fortunately, this phenomenon is only noticeable close to the speed of light. Imagine yourself alongside early 20th century science fiction swashbuckler Flash Gordon. When not fighting the bad guys or trying to escape from some monster, you're dashing around the galaxy at incredible speeds. While you are, your clock and those back on Earth are running at different speeds. Assuming you've been gone for the better part of a year, when you get back, everyone you knew will have been dead thousands of years. It's the ultimate example of relative time. But Einstein isn't finished quite yet. He still has to conjure up the most famous equation of the century, E equals mc squared.
Einstein realized that not only does time slow down the faster you go, he also realized that when objects move, they get heavier as they move. It was a curiosity. Why should objects get heavier as they move? And then he suddenly realized that the reason why objects get heavier as they move is because the energy of motion is being converted into mass. Now think about that for a moment. The energy of motion is being converted into mass. This means that energy is turning into mass, and mass is turning into energy. And Einstein quickly wrote down, it's only one step, quickly wrote down the equation that relates energy to matter, and it is exactly E equals mc squared.
Einstein's theory of space and time is called special relativity. Physicists are intrigued, but little changes in Einstein's life. With a growing family to support, he remains at the patent office and moves on to another, even greater intellectual challenge. Special relativity applies to objects moving at constant speed, but most movement involves acceleration, speeding up or slowing down. So Einstein sets out to extend relativity to cover accelerated motion. It turns out to be one of the hardest problems any scientist has ever taken on. Einstein struggles with it for 10 years.
Now, most of us physicists, when we grapple with a problem that we can't understand, we give up and say, God is malicious. He's a nasty God. He's giving us problems that no human can understand. Einstein didn't have that philosophy at all. He didn't say that God was malicious, teasing humans with problems that were beyond human ken. He said God is subtle, that only if we dare to penetrate into the essence of things, then we would find the answer.
To get to the essence of accelerated motion, Einstein once again turns to a thought experiment.
Imagine this elevator were located in deep space and uniformly accelerating upward. With no windows and no connection to the outside world, Einstein said it would be impossible for us to determine whether or not we're moving. But you might say, I feel the pressure on my feet. But his response to that would be, but how do you determine whether that pressure is caused by the elevator moving upward through space with uniform acceleration, or by the elevator simply sitting on the surface of the Earth and you're feeling the effects of gravity?
The fact that you can't tell the difference, says Einstein, means acceleration and gravity must somehow be the same. He concludes, after a series of incredibly complex calculations, that this is only possible if space and time are curved. According to Einstein's theory of general relativity, the curvature of space is caused by the presence of massive objects. Newton had it right that a body in motion tends to stay in motion in a straight line, the shortest distance between 2 points. But in curved space, the shortest distance between 2 points is a curved line. An object experiences acceleration around the curve as gravity. The Earth orbits the Sun not because of a mysterious force, but because the Sun curves the space around it. The Earth is simply traveling the shortest path through curved space. Einstein's theory of general relativity perfectly describes the motions of planets, stars, and galaxies, both in space and in time.
Suddenly, physics could say something about the fate of the universe. It could ask questions about whether the universe as a whole had a certain curvature, whether it would come back in on itself, whether it would expand out forever. General relativity had a scope as infinite as the universe.
The world is not the same place once you understand these theories. Space and time are somehow the same thing. That's very different from my experience as I go through life. And I can never go back to looking at things the way they were before I understood this theory.
In 1921, Albert Einstein is awarded the Nobel Prize for Physics. But it isn't for his work on relativity. Apparently, that's too weird for the awards committee to accept. Instead, Einstein is honored for other contributions, including a paper on the nature of light. This paper ultimately leads to a second revolution in physics, only this time it's too weird for Einstein himself to accept. It's called quantum mechanics. Quantum mechanics comes out of the struggle to understand the structure of atoms. What physicists in the early 20th century learn is that in the world of the very small, the seemingly impossible is commonplace. Things don't exist until someone looks at them. We're unable to say exactly what path something takes to get from point A to point B. Uncertainty and chance are woven into the very fabric of existence. One of the key figures in the quantum revolution is a young Dane with a tendency to mumble. He's the scientist on the right. His name is Niels Bohr. And from childhood, it's physics that consumes him. Once, while playing goalie in an important soccer game, he starts scribbling equations on a goalpost. Only the screams of an ardent fan snap him out of his reverie in time to stop an opposing player's potential goal. At school, he's an excellent student, though he seems to have a serious phobia about writing. As a graduate student, he dictates his entire doctoral dissertation to his mother, causing a family fight when his father insists that the budding PhD learn to write for himself. He never does. After his marriage, his wife gets the job. In 1912, shortly after receiving his doctorate, Bohr travels to England. He comes to Ernest Rutherford's laboratory just 1 year after Rutherford makes a startling discovery about atoms. Atoms had been seen as amorphous blobs of positive charge studded throughout with negative electrons. In fact, Rutherford says, they're more like little planetary systems. All the positive charge and virtually all the mass is concentrated in a tiny nucleus, around which the electrons orbit like planets around the sun. This is the courtyard at Cambridge University, where Rutherford began and ended his scientific career. Imagine an atom this size.
If we think of that being the size of an atom, then the size of the nucleus would only be 1 millimeter in diameter. That's a bit smaller than this little grain of sand that I've got in my hand here. In other words, what it means is atoms are essentially empty space.
Now, how can we reconcile that with the fact that matter is matter, and my hands don't go through one another? Well, that's crazy, because if it's mostly empty space, they should pass right through one another. Well, what we understand now is, in fact, that the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields. When the electrons come within a very small distance of each other, they begin to repel each other. So we have the illusion that things are solid, when actually we have this tremendous vacuum given by the fact that the atom is basically empty. Now, this means that I'm not really sitting in this chair at all. The atoms of my body are about 1 angstrom hovering over the atoms of this chair.
Rutherford's conception of the atom is a breakthrough, but almost immediately he finds a paradox at the heart of it.
See, the problem was that if you've got a nucleus with a positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second. That's a very secure prediction of classical physics. And that's catastrophic. What it's telling you is that atoms cannot exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with the large volumes that they have.
When Niels Bohr arrives in Manchester, Rutherford is ready to abandon his model of the atom. But Bohr sees a way to save it.
He was so excited, he canceled his honeymoon. He had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was that you would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory, but only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the sun, no problem. It would have a different orbit, would be stable, would have a different time to go around the sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
Bohr's idea that electrons can have only certain orbits draws inspiration from other new theories that suggest heat and light come in units that can't be divided, called quanta. But applying this quantum idea to matter is practically sacrilegious. In fact, most physicists disapprove of Bohr's theory. Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others.
If it's not nonsense, at least it doesn't make sense.
This is just a cheap excuse for not knowing what's going on.
The assumptions are too bold, too fantastic. They can't be right.
In time, two camps emerge. A group around Bohr, which believes in his so-called quantum theory of matter, and those who cling to the classical view. No less than the true picture of nature is at stake. In 1926, Werner Heisenberg, a 25-year-old German physicist, comes up with a mathematical description of atoms that goes a long way toward legitimizing Bohr's view. Classical physicists remain unconvinced. Heisenberg's mathematical matrices are too complex, and the mysterious comings and goings of electrons are just too hard to imagine. Within a year, an Austrian named Erwin Schrödinger offers an alternative.
Schrödinger had this beautiful theory of the electron as a wave. It was smeared out over space and time. It wasn't a particle at all. Physicists loved this idea. We had a physical picture. We could look inside the atom. Physicists knew how to calculate with waves. They calculated waves as an undergraduate in college. They knew how waves went around and formed orbits. So the appeal of the Schrödinger picture was that it was pictorial. It was almost Newtonian. It was continuous. None of this quantum business. And you could calculate with it.
So which is it? Is matter made up of waves or particles? They seem to be complete opposites. Waves can pass through one another, sometimes canceling each other, sometimes making even bigger waves. But particles, on the other hand, bounce, smash, exert force when they meet. They can't cancel each other out.
So these two pictures clashed with each other, and they debated. And they had arguments, and they yelled and screamed at each other. In fact, one day, Heisenberg was so worried that he simply came down with hives and hay fever and tremendous case of allergies, worrying about whether or not the rival picture was correct.
In 1926, Bohr and Heisenberg invite Schrödinger to Bohr's new institute in Copenhagen to try and work out their differences. Heisenberg writes about the visit.
Though Bohr was an unusually considerate and obliging person, he was able in such a discussion to insist fanatically and with almost terrifying relentlessness on complete clarity in all arguments. He would not give up, even after hours of struggling, until Schrödinger had admitted that his interpretation was insufficient. Every attempt from Schrödinger's side to get around this bitter result was slowly refuted, point by point, in infinitely laborious discussions.
Bohr's wife nurses Schrödinger when he falls ill from exhaustion. She brings him tea and cake, even as her husband sits on the edge of the bed continuing the argument. Still, Schrödinger clings to his classical view, wearily noting at one point, if one has to go on with these damn quantum jumps, and I'm sorry I ever started to work on atomic theory.
The essence of the Bohr-Heisenberg picture was that the electron was a particle. However, there was a certain amount of uncertainty with regards to where the particle was. Now, one day, Heisenberg was so paralyzed, worrying about all these problems, that he took a walk in the park. Outside his institute, there's a famous park, and late at night, he walked through the park wondering, how can it be? How can it be that you don't quite know where the electron is? And then in a flash, he understood. Because to understand where an electron is, you have to look at it. To look at it, you have to shine a light on it. But when you shine a light on it, that disturbs where the electron is. So the very fact of observing an object changes its location. Therefore, he realized that uncertainty is an essential part of his picture.
Heisenberg calls his insight the uncertainty principle. In a clear mathematical way, it says, the more you know about a particle's position, the less you can know about its speed and direction. And the opposite is also true. The more you know about a particle's speed and direction, the less you can know about where it is at any given time.
And when he finally had that idea, he realized that he could merge the Schrödinger picture with the Bohr-Heisenberg picture to give us the modern-day theory of the quantum principle. In other words, the electron is a point particle, but you don't know quite where it is. And the probability of finding it at any given point is given by a wave, the Schrödinger wave. So we now have this beautiful synthesis of waves and particles.
Heisenberg's principle, indeed, is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work. Suppose I have a laser beam here. And I use laser beam because that's right, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit. And here goes the laser beam right through the slit. Light goes on, and here I project this onto this wall or screen, projection screen. And what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
According to the quantum theory, even the most bizarre events have a probability of taking place. There's a certain probability that I will dissolve and simply rematerialize on the other side of that brick wall. Now, you may say to yourself, well, that's impossible. We've never seen anyone dissolve and rematerialize on the other side of brick walls. But we actually give this problem to our graduate students. To our PhD candidates, we ask them to calculate, using the quantum theory, what is the probability that you will find yourself on the other side of a brick wall? Now, to tell you the truth, you would have to wait longer than the lifetime of the universe for such an event to take place. So you don't have to worry. Your atoms are not going to dissolve, and you're not going to rematerialize on the other side of brick walls. But there is a probability you can calculate for that event happening.
And then you can ask yourself the question, do I understand it? I don't even know what that means, understanding. I have problems with that. Physics describes things, describes phenomenon. And as long as it is predictable, as long as that formalism applied in a certain situation gives you the right answer, who cares? Who cares what the meaning is of understanding? I think I leave that up to philosophers. And I think they don't have a clue either, of course, but they... Yeah.
There are some physicists who refuse to accept that quantum mechanics represents the full story of the subatomic world. The most famous is Albert Einstein.
Quantum mechanics is very worthy of regard, but an inner voice tells me that this is not the true Jacob. The theory yields a lot, but it hardly brings us any closer to the secret of the old one. In any case, I am convinced that he doesn't throw dice.
He couldn't believe that there were big patches of the world about which we could not know. And his idea from early on in his life, all the way to the end of his life, was that there ought to be a set of equations, deterministic, causal, ordered, formulated in such a way that they could tell us everything about a future in terms of everything about the present. And quantum mechanics wouldn't allow it. He couldn't stand that idea.
The world's greatest physicists gather in Brussels in 1927. Einstein challenges Bohr and the idea that uncertainty rules the world. Werner Heisenberg writes in his diary,
"We all stayed at the same hotel. The discussion usually started at breakfast, with Einstein serving us up an imaginary experiment by which he thought he had definitely refuted the uncertainty principle. In the course of the day, we would have discussions on the matter, and as a rule, by supper time, we would have reached the point where Niels Bohr could prove to Einstein that even his latest experiment failed to shake the uncertainty principle. Einstein would look a bit worried, but by next morning he was ready with a new imaginary experiment more complicated than the last."
One of Einstein's challenges is so clever, it has Bohr deeply concerned for the future of quantum mechanics. Physicist Leon Rosenfeld writes,
Bohr did not see the solution. I shall never forget the sight of the two antagonists leaving the hall. Einstein, a tall, majestic figure, walking quietly, with a somewhat ironic smile, and Bohr trotting near him, very excited. During the whole evening, Bohr was extremely unhappy, going from one scientist to another, trying to persuade them that it couldn't be true, that it would be the end of physics if Einstein were right.
Bohr spends a sleepless night in his hotel room before he discovers a flaw in Einstein's argument. Ironically, it involves a subtle application of Einstein's own theory of relativity.
Bohr and Einstein are an astonishing pair. In many ways, they loved each other. They loved talking to each other. They loved engaging with each other's ideas. And yet they wanted such utterly different things from physics that they never really could see eye to eye.
God does not throw dice was Einstein's unshakable principle, one that he would not allow anybody to challenge. To which Bohr could only counter, nor is it our business to prescribe to God how he should run the world. Einstein and Bohr have their last battle about quantum mechanics in 1933. By this time, both relativity and quantum theory are almost universally accepted by physicists as the most powerful ideas they have for explaining the world. Now, attention shifts to another challenge, figuring out what goes on inside the atom. Physicists want to know what holds the nucleus together. They want to know if protons, electrons, and the newly discovered neutrons make up everything in the universe, or if these particles are made up of something even more fundamental. In the process, what begins as an intellectual quest turns out to have explosive consequences. In the early 1930s, Albert Einstein emigrates to America to escape the rising tide of fascism and anti-Semitism in Germany. Before the decade ends, many of Europe's finest scientists are forced to make the same journey. Among the last to leave is Niels Bohr. He arrives in the United States in 1939, bringing with him stunning news. In Hitler's Germany, two scientists have split an atom of uranium, releasing in that moment some of the tremendous energy bound up in matter. Using simple equipment widely available, they produced the first evidence from a controlled experiment of Einstein's famous equation, E equals mc squared.
I was in Berkeley, and people had gone to the meeting in Washington where Bohr brought his news, and they called up and said, gosh, this is amazing, can you do it? And in a day or two, 2 or 3 people had done it.
No longer any doubt about it. That uranium...
I could see the big spikes of fission on the oscilloscope screen. And by the end of the month, everybody knew this was going to be a wartime device.
At a super-secret facility deep in New Mexico's scrubland, the U.S. Army assembles a team of American and transplanted European physicists, the greatest collection of scientific talent the world has ever seen. Their challenge? Create an atomic bomb before the enemy.
We were galvanized by the notion that the Germans were ahead. They had spent a lot of money, they were very good, they were discovered in Germany, they had able people. Actually, we didn't realize that they had lost so much by destroying the community as they had done. It was lucky.
Americans have the talent and practically unlimited resources. In less than 5 years, $2 billion creates a nuclear project the size of the U.S. auto industry. Yet until the very end, no one can say for sure the product of all this effort will work.
The basic physics was known. The quantum principle was known. Relativity, E equals mc squared, was known. The chain reaction was known. But it was not known how to put it all together. So these physicists, some of the brightest minds of the world, were concentrated at Los Alamos not to discover new physics, because that was already done by the Bohrs and by the Einsteins. They were assembled to see whether or not it would actually work.
When I first brought the plutonium sphere in contact with a high explosive, I was quite scared about high explosive. And Roger Warner, who was in charge of that particular assembly, he was calm and he said, don't worry about it. He said, you can't run very far in a millisecond anyhow, so you'll never know what happens if it goes off wrongly. It was a new world. Everyone could see that. Maybe it would bring an end to the war. That was very good, but who knows what was going to come after that? We didn't know. We should have known more than we did, but we didn't.
It was this fantastic experience of taking theories that were equations, and building something of enormous power, the power of the sun. But just like the opening of Pandora's box, perhaps humanity was not ready for cosmic fire. Perhaps humanity was not mature enough to handle the power of the sun now being placed on the earth.
There's a universe up there that we can't see with our eyes, even if we have something 1,000 times larger than this. We have to turn to a different kind of telescope, one without lenses or mirrors or any of the other things astronomers have relied upon for centuries. This invisible universe has to be seen with telescopes that use radio waves, X-rays, infrared rays, or gamma rays. Everything in the universe gives off radiation of some kind. For example, the glaze on this teacup emits gamma waves. Imagine that it is a galaxy, and this Geiger multitube, a crude ray telescope. In the second half of the 20th century, astronomers start exploring the heavens with instruments that are sensitive to a number of different forms of radiation. And when they do, it's like lifting a veil from the face of the universe. One of the most surprising discoveries of post-war astronomy is made with this device built outside Cambridge, England. It may look like 4.5 acres of laundry line, but it's really a radio telescope. As the Earth rotates, miles of antenna wire receive radio signals day and night. When it goes into operation in 1967, Jocelyn Bell gets the task of running it. Within months, the young graduate student notices something she's never seen before. It's a funny blip on one of the long rolls of chart paper used to record what the telescope sees.
The first few times I saw it, I just put a question mark by it and passed on. But I think the human brain stores problems. I think mine does anyway, things that it can't resolve, things that it can't cope with. Because this curious little signal occupied about 1/4 of an inch in 400 foot. And yet somehow my brain stored that, way back somewhere, but it stored it. And after it had dealt with this problem a couple of times, and it faced it the third time, it said, I've seen something like this before.
She immediately calls her thesis advisor, radio astronomer Anthony Hewish. He's intrigued, but cautions the signal is probably man-made. Bell goes back to her charts and figures out when the signal should come again. She sets her instruments to record a more detailed image and discovers the signal is a string of pulses exactly 1 1/3 seconds apart. Never before has a telescope of any kind found something like this. It's a complete mystery. Heavenly bodies don't just pulse on and off.
Look at the sun. The sun doing this. Look at the moon. Is the moon doing this? Look at all the stars in the sky. Look at them with your naked eye. Have you ever seen one go? Nothing, right?
And one way out, it didn't explain everything, but one way out was to say, well, maybe it's little green men sending a signal to us.
I think they were totally shocked, shell-shocked that this possibility existed. They realized it would be the discovery of the century. If we get in touch, somehow receive signals from civilizations.
What do you do if you have really picked up signals from another civilization? Do you tell the president, the press, or the Pope first?
Before they can tell anyone anything, Bell finds what could be a second signal. She heads out to the antenna on a cold November night to check it out.
And I came out on my scooter, slithering all over the place on the ice. And when I got here, the machinery wasn't working properly because of the cold. But I flicked switches, I kicked it, I cursed it, I breathed hot air on it, and I got it to work for 5 minutes. And it was the right 5 minutes, and it was the right setting, so as it was looking at the right bit of sky. And in came whoop, 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 whoop. Very like the first lot, but not totally the same. A little bit different, 1 1/4 seconds instead of 1 1/3. And that settles the little green men question, because it's so unlikely there'll be 2 lots of little green men, opposite sides of the sky, both deciding to signal to an inconspicuous planet, and using a not very intelligent way of doing it also. So it had to be something stellar.
The news of Bell's pulsing stars spreads rapidly through the astrophysics community. It is clearly an important discovery. What they are and how they pulse is a real mystery.
Formed in a rotating medium. So if you take a large object collapsing and it rotates enough, then you go back to the old argument that we had, that maybe it breaks up.
Perhaps it's a white dwarf. Perhaps the residue doesn't get to the...
Finally, a physicist connects what Bell has found with an old theory about the death throes of stars. This theory, long assumed to be untestable, predicts that when a large enough star runs out of nuclear fuel, it will collapse and crush the atoms within it. What's left is like nothing else in the universe, an incredibly dense object made almost entirely of neutrons.
Every open space that you can think of between electrons in the atoms is squeezed out, and it becomes one huge nucleus. And the electrons are pushed into the protons, forming neutrons. That's why we call them neutron stars. A neutron star has typically a radius of about 10 kilometers, 6 miles. But the amount of matter in a neutron star is a little bit more than the total mass, the total matter that we have in the sun. A spoonful of this neutron star matter would weigh, if you like the word weighing, in pounds, it's 2 times 10 to the 11. It's a 2 with 11 zeros pounds in one spoonful.
Neutron stars can rotate up to 700 times a second. As they do, their powerful magnetic fields rip through space, blasting radio waves outward like a galactic lighthouse. It's that beacon that Jocelyn Bell sees with her radio telescope. Theory had said that neutron stars are possible, but for decades, astronomers and physicists clung to the view that they're just too weird to be real. Bell's discovery is dramatic confirmation that the universe is stranger and more fantastic than anything we experience in our corner of the cosmos. The reality of neutron stars stirs excitement that black holes may also be real. They are perhaps the most fantastic and unlikely prediction ever made by physicists. World War I had just broken out when Albert Einstein publishes his general theory of relativity. Among those fighting on the Russian front is a German astronomer and physicist named Karl Schwarzschild. With the war raging around him, Schwarzschild discovers that Einstein's equations predict the existence of a star so unimaginably dense that even light cannot escape it. From the battlefield, he sends Einstein his calculations. Just weeks after receiving Einstein's reply, Schwarzschild dies on the front lines. Einstein marvels at Schwarzschild's work, but he never accepts that such a star could really exist. As he puts it, it just doesn't smell right. Through the 1960s, most scientists agree with Einstein. But the public is completely taken with the idea of a dark star from which escape is impossible, and where time and space cease to exist.
We are falling. Towards what, I wonder?
Zen, put forward coordinate 890 on visual.
Confirmed.
But there's nothing there.
Zen, use long-range intensifier. 3 guesses, if you need them.
A black hole. My God. We're falling into a black hole.
The existence of a real black hole is almost impossible for physicists to accept. Yet many have to admit that the process that creates neutron stars should also create black holes.
When a star has burned up all its nuclear fuel and there is no longer heat that pushes it out, that the core collapses and it can form a neutron star. This collapse can be so strong, depending upon the original mass of the star, that it overshoots and doesn't become a neutron star, but become even smaller. And then it can become a black hole. If you take the Earth, to give you an example, and you take a vise, if you could make a vise and you squeeze the Earth has a radius of 6,400 kilometers. If you could make the radius 3 centimeters, the Earth would become a black hole. 3 centimeters, this big. Then it would automatically further collapse onto itself. Nothing could stop it, and it would become a black hole. And you could never, light could never leave it, radio waves could not leave it, because they all go with the speed of light.
Finding something that doesn't give off light or any other kind of radiation is tricky, to say the least. It's not until the early 70s that astronomers stumble on the first indirect evidence of a black hole. The first clue comes when X-ray telescopes reveal an area of intense violence and temperature in the constellation Cygnus. Paul Murden is one of many astronomers who begin to focus on this area. Working with Louise Webster, he finds a supergiant star orbiting something they can't see. Logically, the supergiant must be circling a much smaller and denser star. One so dense, its gravity is sucking huge amounts of matter from its larger companion. Only this could produce the intense X-rays other astronomers had detected. Further measurements reveal the small star's gravity must be greater than anything discovered before. The only explanation is a black hole. There is still no absolute proof that black holes exist. But from the 1970s on, most scientists have come to accept them as real. Incredibly strange, but real.
Because with a neutron star, at least you can imagine it has a surface. And you can land on that surface. And okay, it is a mind-boggling magnetic field, all right, but so be it, it's there. And okay, it rotates 700 times per second. But a black hole has no surface. So you can't even talk about a surface that rotates around. It doesn't exist. And there is no time that you can define. That is pretty bizarre. That goes beyond, totally beyond my imagination. I'll be very honest with you. But yet, it's one of my specialties. I measure them, I find them. Can I envision them? No.
Current theory holds that there are billions of black holes in the universe, including enormous ones at the center of most galaxies. These are so large, they must have devoured millions, perhaps even billions of stars. But even the birth and growth of black holes are nearly as fantastic as the creation of the universe itself. For most of human existence, the question of how everything began is one that only religion dared to answer. But with Edwin Hubble's discovery that the universe is expanding, some scientists begin to believe that they too might have something to offer. Their reasoning goes something like this: if the universe is expanding, then in the past it must have been smaller. Go far enough back, and everything must have been crunched together at a point of infinite density. Our universe began, they suggest, when that point exploded, creating the expansion we still see today. This vision comes to be called the Big Bang theory of creation. At the start of the 1960s, scientists are equally divided between this Big Bang theory and a competing notion that the universe is eternal, called the steady state theory. But there's no real hard evidence for either one. In fact, almost no one expects the debate will ever be resolved. In the early 60s, Robert Dicke, an astrophysicist at Princeton University, comes up with what he thinks is a way to test whether or not the universe started with a Big Bang. He's convinced that if it happened, the entire universe should be filled with radiation left from the moment of creation.
Bob Dicke's reasoning was quite interesting. He reasoned that if the universe had gone through this Big Bang phase, it must have been very hot and very dense, and there must have been a lot of heat radiation, very high temperature. And he couldn't find any theoretical way to get rid of this radiation. It must still be around. It's cooled off because the universe expanded, but it must still be around and in the microwave band, the band where radar works.
It's a truly amazing possibility. 15-billion-year-old heat transformed by the expansion of space into low-level radio static that permeates every corner of the universe. If it's there, the only cosmological theory that can explain how it got there is the Big Bang.
The nice thing about Dicke's theory is...
Dicke convinces David Wilkinson and another young physicist to build an antenna and search for this cosmic background radiation.
...on a very specific curve called the black body curve.
We weren't in any particular hurry because Bob Dicke's idea was so original. We weren't too worried about somebody else getting there before we did. So we charged ahead rather slowly. We had no microwave equipment at all. We had to order things new. We went down to Arch Street in Philadelphia and dug around in the World War II surplus shops to find things that were cheap. Bob Dicke is a rather frugal experimentalist, so if we could find it in the junk shop, we did that.
This is the antenna that resulted. It's carefully calibrated using super-cold helium. While Wilkinson is building it, two other scientists, just 30 miles away, are setting up an experiment that seems to have nothing to do with the Big Bang. With colleague Arno Penzias, Bob Wilson plans to use this microwave antenna to study our galaxy. He's unaware of Dicke's idea. In fact, he doesn't believe in the Big Bang, but prefers a universe with no beginning or end.
I like the steady state. It is philosophically satisfying because there's no end to the universe in the future. It goes on forever in the same sort of state that it is. And there's no beginning for it either. So physicists generally like steady state because they don't like to have a time beyond which they can't know anything.
Wilson and Penzias are then just getting started on their scientific careers. They have no desire to confront a problem as difficult as whether or not the universe had a beginning. They just want to make some small contribution to astronomy.
Doing science by ourselves was a great new adventure. We sort of had a chance at Bell Labs to become scientists, in the real sense, and make use of this unique instrument. And we really devoted ourselves to it.
Wilson and Penzias believe the Holmdel antenna will make a great radio telescope because it's designed to reject all extraneous signals or noise. But from the very first time they use it, extraneous noise is exactly what it seems to be picking up.
Every time we started up, we saw the same noise level. Everywhere in the sky we pointed, we saw the same noise level.
It isn't a lot of noise, but they fear it's enough to compromise some of their research. So they decide to find out what's causing it and get rid of it. They check to see if it's there at night. They check to see if it's there in different seasons. They check all possible ground-based sources of radio noise. They check the antenna itself and tape all its joints. they double-check every piece of equipment in the system, and the noise is always there. With few alternatives left to try, they decide to check a real long shot.
A set of pigeons had started roosting up in the throat of the thing, and of course they'd coated it with the same white pigeon droppings that you see on statues and so forth in the city. We got a ladder from the carpenters and a couple of push brooms and some scrub brushes, and scraped off the difficult ones and swept the whole thing out.
They check again and realize they could have left the pigeons alone. A year of this struggle has left them convinced the antenna is fine. The only possibility left, and it doesn't make sense, is that every corner of the universe is filled with the same noise. Desperate, they begin calling other astronomers for help, and one suggests calling Bob Dickey.
The phone rang, and Bob picked it up, and it was two guys from Bell Labs who had a problem, which at first didn't seem to have anything to do with us.
We didn't learn very much on the telephone, but they agreed to come out and see what we had done and tell us about what they had in mind.
He hung up the phone, and I'll never forget exactly what he said. These are his exact words. He said, "Well, boys, we've been scooped."
Robert Wilson and Arno Penzias had already heard the echo of the Big Bang. Their annoying background noise was, in fact, nothing less than a whisper from creation itself. In the beginning, some 15 billion years ago, the universe exploded from a single point. Less than 1 minute later, it's 1 billion miles across. Though cooling rapidly, it still has an average temperature of 1 billion degrees. The universe continues to expand and cool. Gradually, gravity draws together atoms, and then clumps of atoms. It takes 1 billion years before stars form and galaxies are created. Eventually, around some of the stars, planets form. And on at least one, life begins. If everything in the universe began in a single point, it's hard not to wonder what it took to go from such ultimate simplicity to all of this. Many physicists believe that at the beginning of time, there was only a single particle governed by a single force. From that starting point, within a tiny fraction of a second, particles like protons and electrons evolved, and forces like gravity and magnetism came into being. But did the universe have to be like this? Could it have turned out any other way? Perhaps if we can work back to the moment of creation, to that ultimate particle and force, we will come to understand why the universe is the way it is, and even to express it in what physicists call the final theory, which it's hoped can be captured in a single equation that can fit on a t-shirt. This may explain everything. When we look at nature, we see the complexities, the differences among things. But scientists tend to look for the connections, the simplicity that lies at the heart of it all.
The more you learn about nature, the simpler it looks. And that's why I think we will find a final theory. Because although I can imagine things getting infinitely more complicated, complication without end, I can't imagine simplicity without end. The whole progress of physics has been toward a more and more simple description of nature. And how simple can things get? Simplicity must finally terminate. There must be something so simple that we can't imagine anything more simple.
But in the years following World War II, physicists are stunned to find their dream of ultimate simplicity slipping away. Experiments meant to reveal simplicity find ever greater complexity.
Berkeley, California, home of the Bevatron. The BeV stands for billions of electron volts, world's most powerful atom smasher.
It's the beginning of the era of big science. Giant atom smashers are built to accelerate subatomic particles to fantastic speeds and smash them into other atoms.
Each new accelerator built after the war was more powerful than the one that came before. Each was able to ram particles into each other harder and to show what was happening at a smaller and smaller scale. It was just like the telescopes. With each new telescope that was built, you could see further out into space, gather more light, resolve objects more precisely. With each new accelerator, people were able to see deeper into matter, more precisely, better resolution, smaller scale.
Photographs of the tracks of the objects produced in these accelerators reveal a multitude of new particles that seem just as fundamental as the familiar proton, neutron, and electron.
We were literally drowning in subatomic particles. One year, out of sheer frustration, J. Robert Oppenheimer, father of the atomic bomb, stated that the physicist who does not discover a new particle that year should win the Nobel Prize in physics.
There were hundreds and hundreds of particles which looked just as elementary as the proton. It became clear that if elementary meant anything, either there was something more elementary inside these particles, or perhaps they were all elementary, a frightening idea.
Among the physicists unhappy with all this complication is a brash young theorist named Murray Gell-Mann. By the age of 25, Gell-Mann is already well known in the world of physics for his encyclopedic interests and knowledge, his quick and creative mind, and his frequently abrasive personal style. A colleague says of him, Murray has no particular talent for physics, but he's so smart, he's a great physicist anyway.
The important thing is first to steep yourself in the problem, to look at the puzzle, all the pieces of the puzzle.
By looking for patterns and symmetries, Gell-Mann finds a way to organize all the newly discovered particles into families. Then, inspired by a chance encounter during a visit to Columbia University in New York, he takes a giant step toward simplicity.
Over lunch, a physicist approached him and said, "Isn't it possible that your theories could be explained by postulating 3 even more fundamental particles?" Well, everyone at that table dismissed that idea immediately, and they patiently explained to this physicist what was wrong. You would have fractionally charged particles, an outrageous, ridiculous idea, because everyone knew that particles were either +1 or -1 in charge, never 1/3 or 2/3.
But over the months that follow, Gell-Mann grows to love the idea of this deeper level of reality. The fact no one's ever seen particles this bizarre, he decides, isn't his problem. In early 1964, Gell-Mann proposes to the world the existence of 3 new fundamental entities he calls quarks.
His 3 quarks could combine in different ways to reproduce the properties of this enormous particle zoo. It would simplify, organize, predict It was a great scientific advance. The problem was that no one had ever seen anything that looked like a quark.
Now, what are the quarks? Are they actually real objects? Well, my experimental friends are making a search for them in all sorts of places. One atomic spectroscopist friend of mine calls me up sometimes at midnight to report his progress in a search for quarks in seawater. Most things with curious chemical behavior in the ocean end up eaten by oysters. And so now he's grinding up oysters and looking for the atomic levels in the oysters. So far, though, no quarks.
Physicists were faced with a paradox. Where were the quarks? Everywhere we looked, we could not find any physical evidence for the quarks. And in fact, some physicists even began to doubt the correctness of the theory. However, over the years, indirect evidence began to trickle in, confirming this theory.
And now when experimenters take a hard look at the proton, they see strong evidence of the quarks inside, and also of the gluon.
Quarks may be real, but they're still pretty strange. For starters, they're so small, it's hard to apply to them our normal notions of size. Physicists describe them as points.
Points? Come on. What do you mean points? How can something have a mass and a charge and be a point? Well, it takes a few muscles in the mind that haven't been worked on. But if you work on them for a while, you can imagine such an object. It's a little bit like Alice in Wonderland. Remember the Cheshire cat sitting on the tree, smiling, and Alice is noticing that the cat is disappearing in front of her eyes, and poof, when the cat disappears, the smile is left behind. You remember that? Well, in a way, you can look at that as you take a quark, and it's spinning, and it's a spherical, if you like, and it has mass and charge and spin and all these other properties that we like to measure about it. But in front of your eyes, it's shrinking. And finally, it poof, shrinks to a point, leaving behind its spin, its charge, its mass, and if it has a smile, leaving behind its smile. That's the idea of point particles.
With quarks, physics' journey into the heart of matter takes a giant step toward its goal of finding an ultimate particle from which everything is made. Instead of hundreds of fundamental particles in nature, now there are simply 3: electrons, quarks, and neutrinos, tiny particles with almost no mass that rarely interact with the stuff we're made of. The search for a single fundamental particle is matched by the search for a single force that governs the behavior of everything. This was Albert Einstein's great quest for the last 25 years of his life. More than once, he thought he had done it, only to learn his solution was fatally flawed. When Einstein was working on unification, he recognized 2 forces, gravity and electromagnetism. But today, physicists have to deal with 2 others, the strong force and the weak force.
The weak force is responsible for many forms of radioactivity. The strong force holds our nucleus together. The nucleus is full of protons, which all have positive charges. And if there was nothing to hold them together, the electric forces would make them fly apart, because equal charges are repelled. The strong force prevents that from happening.
One of the physicists who plays a key role in the quest for unification is Steven Weinberg. His specialty is the 2 forces within the atomic nucleus, the weak and the strong.
Like a lot of other physicists, I got started with chemistry. I had a hand-me-down chemistry set that was given to me by an older cousin. First, I just liked to play with the powders and the liquids and make colored smoke and things like that. And gradually, just reading about it, I became aware that what went on inside an atom was something that couldn't be explained in terms of ordinary things that I knew about in everyday life. And I got the feeling there was something strange and wonderful about physics, which was the science that governed what goes on inside atoms.
That feeling about physics stays with Weinberg through college and grad school. In the late 60s, he's struggling unsuccessfully to use certain mathematical ideas to make sense of the strong force, the one that holds atomic nuclei together.
And then at a certain point, I think when I was driving my car to MIT, I realized, my goodness, this kind of mathematical idea, although it's a complete loser as far as the strong forces are concerned, is just what we need to make a theory of the weak force. And to my surprise, although certainly not my disappointment, what came out at the end was not just a theory of the weak forces, but inevitably a unified theory of weak and electromagnetic forces.
All of a sudden, from 4 fundamental forces, we now had 3 fundamental forces. And this changed the entire terrain of theoretical physics.
In order to test Weinberg's theory, the European community spends a staggering $150 million to modify and make more powerful its largest particle accelerator.
The protons are in the machine. We're now in the countdown.
In the subatomic shrapnel created in these collisions lies the evidence that confirms the correctness of the electro-weak unification. The 4 fundamental forces are now 3. But just as 3 types of particles doesn't satisfy, neither does 3 forces. In the mid-1980s, work begins on what most physicists believe is the key to getting even closer to the heart of matter. It's called the Superconducting Supercollider, or SSC. With an underground particle ring 50 miles long, it's designed to recreate the conditions of the universe in its first trillionth of a second.
It was to be a device so large it would enclose towns inside it. It was a machine that would require buses to get from one part to another. It was a machine that would ship volumes of data equivalent to the entire Library of Congress out to distant laboratories around the world with amazing frequency. The detectors, the sites where the actual physics would be conducted, would cost $1 billion apiece and have somewhere near 1,000 physicists and probably an equivalent number of technicians at each one.
But in 1993, after an investment of $2 billion, construction on the SSC is halted. Years of escalating costs have eroded congressional support. The message to scientists is, find another way to hunt for the ultimate particle and the ultimate force. Physicists are devastated.
When the American particle physics community gambled on the SSC, they had essentially to shut down program after program in the hopes that they could convince the politicians that by making these sacrifices, they should receive the amount of funds necessary to build the superconducting supercollider. When the SSC was canceled, they essentially lost everything.
Even still, the search for unification goes on. In the 1980s, theorists proposed that at the heart of everything are infinitesimally small vibrating strings. String theory, quite simply, is the most exciting idea to hit physics since the days of Einstein and Bohr. It may well be the final theory, the one that explains absolutely everything.
The Pythagoreans believed that music was the language of nature, that their harmonies on a violin string, which they worked out for the first time in history, were the harmonies of the universe. And they thought that all around us, surrounding us, was music, the music of the spheres. Unfortunately, that idea never got anywhere, because that couldn't explain the elements. Now we think that if I have a super powerful microscope and could peer into an electron, I would see a vibrating violin string. And when that note changes, it changes into a quark. It changes into gravity. It changes into light. So in other words, our bodies are nothing but collections of strings. And the laws governing these strings are the harmonies of the strings, and they are the laws of physics.
Theorists usually imagine strings as incredibly small, closed loops, more like rubber bands than anything else. Ordinary matter, even space, time, and energy, are nothing more than the vibrations of strings. To physicists, they are beautiful, elegant, simple, everything they dream about.
Then when I integrate
But the mathematics needed to describe them is anything but.
y, a, b, c, d, my claim is that this thing that I'm writing on this side of the equation is a supersymmetric definition of an index, and the statement is that the topology of the superspace can only be generated by the topology of the bosonic manifold. Mathematics for a theoretical physicist really is an extrasensory organ. I cannot make myself as small as an atom. I cannot make myself the size of a proton. But with mathematics, I have an accurate representation of that, and then I can use my mind to actually look at those small things. For me, the funny thing...
One of the strangest things about string theory is that it only works if there are 10 or more dimensions.
Some people say to us, but that's not commonsensical. That violates common sense. Well, why should common sense have anything to do with the universe? Why should the universe care about your common sense? So we physicists are prisoners. We are prisoners of experiment, prisoners of our mathematics, and we simply go where the mathematics, go where the experiments take us.
With string theory, they're going way out. They're using mathematics in a way that physicists have never used mathematics before.
In 10 dimensions, we can look at the entire Clifford algebra of the Dirac matrices. So we have the identity.
They're becoming more and more mathematical, more and more esoteric, unfortunately, and most unfortunately of all, further and further removed from experimental verification. But in a sense, it's the only game in town. It's the only hope we have of unifying everything.
What we are talking about now is understanding all four fundamental forces. That's the power of this theory. We're talking about a theory of the universe. Will it give me better color television? The answer is no. It's not going to give you a bigger toaster. It's not going to give you better sliced bread. But it will give you is a theory that will affect the future course of human civilization. Your great-great-great-grandchildren will one day live to harness the power of the unified field theory.
No one knows if string theory is the final theory, but if it isn't, physicists are sure to keep searching.
I think it's almost a religious belief that things must somehow very deep down be simple. And that we are to some degree blind and don't see this simplicity, but are searching for it. Now that's what physics has been doing always. Very difficult processes, very difficult phenomenon, which seemingly are unrelated, chaotic, through simple descriptions, pull them together and unify them. And that will go on for a long, long time.
Astronomers will also keep trying to solve the mysteries of the universe. On a mountain in Arizona, one team of scientists is searching the sky for clues to the ultimate fate of the cosmos. At this and other telescopes around the world, they're measuring light from stars halfway across the universe.
And this is supernova.
Then Bob Kirshner and his colleagues will use those measurements with Einstein's equations to calculate the approximate mass of the entire cosmos.
This is not easy. I don't know what we're supposed to do except just sit there and take it.
If Kirshner finds enough mass, it means the universe will one day stop expanding and will collapse back upon itself in what astronomers call the Big Crunch. If he finds less than that amount, the universe will expand forever into virtual nothingness.
The actual measuring and so on, it's very laborious and it's slow, and you sit there and it takes all night for these photons to dribble in. But the thing that makes it exciting, even thrilling in a kind of quiet way, is that we're after a big question. We're really after a question that people have been interested in for a long time, ever since they could kind of frame the question. What is the fate of the universe? Is it going to last forever? How will things end? These are big questions, and we're really on a path that could give us a concrete answer in the context of how we understand the universe today of which of those possibilities is really the right one. So that's a lot of fun, and it keeps you awake at night.
Calculating the total mass of the universe will also shed light on what may be the biggest question facing 21st century astronomy: the mystery of dark matter. That's matter we can't see, but we know must be out there, because we've measured its gravitational effect on the things we can see. Telescopes as disparate as the newly refurbished 100-inch that George Hale built atop Mount Wilson, to the Hubble Space Telescope in orbit around the Earth, will all be enlisted in the years to come in the search for clues about dark matter.
Theorists believe 99% of the mass of the universe is invisible to telescopes. If that's the case, it's like a modern Copernican revolution. Right? Copernicus told us that the Earth wasn't the center of the universe. Okay? Then we learned indeed that the sun wasn't the center of the universe, and our galaxy isn't the center of the universe. Now we're learning that this dark matter, which may be made of stuff which is completely different than anything we see on Earth, is the dominant stuff of creation. That means if you took away you and me and the stars and everything we see in the universe, the real universe would still be there.
Twentieth century physicists and astronomers have shown us a universe more amazing than we ever suspected, and a reality stranger than we ever dreamed. And the future promises to dazzle us even more. As Albert Einstein wrote many years ago, the most beautiful thing we can experience is the mysterious. It is the source of all true science.